Hello, welcome to the Italian Culture Institute. Welcome to you all, and thank you for joining us for this very exciting networking event and panel discussion, Meet the Rocket Scientists, part of Meet Italy, an Italian and Italian-American networking community in the fields of media, entertainment, economy, technology, and science. It's a forum for the exchange of ideas, knowledge, opportunities, and creative passion, and includes a series of events featuring Italian and local guest speakers of international note. I would like to sincerely thank and acknowledge the presence this evening of our collaborators and guests. The Consul General of Italy, Antonio Verde, the President of the Italian Scientists and Scholars of North America Foundation, a Professor of Medicine, Nephrology, and Hypertension at the USC School of Medicine, Dr. Vito Campese. The co-founder and my partner, Davide Comazzo, Chief Investment Officer for Thalassa Capital, Adjunct Professor of Finance at the Grazie a Dio School of Business and Management at Pepperdine University. Davide. Chair of Silicon Valley Italian Executive Council, SVIEC, our Northern California partner, Jeff Capaccio. And special guest too, CEO and COO of the iconic Italian design firm, Pininfarina, Silvio Angori, the first keynote speaker of Meet Italy, one of the first people to believe in our project. And of course, GPL scientist and co-organizer of this event, Dr. Cinzia Zuffada. Without your partnership, Cinzia, this event would have not been possible. Thank you so much. And of course, as well as the panelists of the GPL, Dr. Sara Susca, Dr. Michele Vallisneri, Dr. and Professor Marco Velli. Thank you so much to you all for your very precious collaboration. Thank you. I would also like to acknowledge the members of Sistema Italia who are here tonight with us. Deputy Italian Trade Commissioner Patrizia Fedele, Italy-America Chamber of Commerce West President Nicola Serraggiotto, Comite's President Eleonora Granata, and I'd like also to acknowledge the presence of several of the brainstormers, Meet Italy brainstormers, and also previous keynote speakers like Marta De Laurentiis, who are here with us tonight. Thank you for attending. We take this occasion also to remind you that next week on the 17th, we have an upcoming event with Federico Rampini. It will be multimedia presentation. It's like a one-man show. He will present his most recent book, which is The Red Lines, Men, Borders, Empires, Geographical Maps that recount our world. So if you're interested, please RSVP. I would like now to invite Dr. Campese to the stage for a few words.
Thank you. Good evening to all of you. It's a great pleasure to be here. Mr. Consul General, dear friends, colleagues, ladies and gentlemen. This year, I'm the president of ISSNAF, Italian Scientists and Scholars in North American Foundation, and this year we celebrate the 10th anniversary of ISSNAF's birth. Over these years, ISSNAF has grown to become the largest and most respected assembly of Italian scientists and scholars in North America. We now count 19 chapters and approximately 8,000 members and affiliates. Why this foundation was created? ISSNAF incorporates some of the best Italian minds in North America in the field of sciences and humanity. Our mission is to facilitate scientific, academic, and technological cooperation amongst Italian researchers and scholars that operate in North America and our colleagues in Italy. As such, ISSNAF is an invaluable resource for Italy and for future generations. Over these years, we have reached out and created strong partnerships with national and regional Italian institutions, with several Italian university industries, other scientific organizations in Italy. We have sponsored dozens of fellowships for young Italian investigators and scholars. We have established Young ISSNAF, an organization within our organization, aimed at promoting programs specifically for young Italian scientists with the goal of supporting the development of their careers here in North America. In June 2018, in partnership with the Fondazione Marche, we held in Ancona the first international expo meeting on Silver Age innovation and technology for a longer and better life. Our future has unlimited possibilities, but all of this cannot be done without the dedication, direct participation, and financial support of all the members and friends. This is a grassroots organization that does not receive financial support from Italian institutions and relies on donation and overheads to sustain its operational structure. On November 7th, to celebrate the 10th anniversary, we will host a gala fundraising event at Drago Centro downtown. The theme to be addressed in this evening is longevity. So if you want to live longer, that's the place to be that night. We will have a limited number of guests. Those of you who may be interested should contact ISSNAF as soon as possible. We are grateful to the organizer of this evening event, and particularly Valeria and Cinzia Zuffada, who is also a member of the board of directors of ISSNAF, and wish all of you a wonderful rest of the evening. Thank you.
Thank you, Dr. Campese. Meet Italy highlights contemporary Italy and the talent and know-how of top Italian executives in Los Angeles, and was created by Davide Comazzo and myself in partnership with the Silicon Valley Italian Executive Council. We warmly welcome now Jeff Capaccio, Chair of Silicon Valley Italian Executive Council, SVIEC, our Northern California partner, who is here with us this evening and will give a few opening remarks. He's also an attorney at Carl and previous regional vice president, a current member of the board of directors of the NIAF, the National Italian American Foundation. Following Jeff, Davide Comazzo and I will introduce the panel. Jeff.
Well, technology and science really make me excited, but basketball is even more exciting to me, and I saw that Danilo Gallinari is here tonight, and I'm a huge fan, so I just thought I'd mention that. And anybody that knows me well knows that that's an absolutely true statement. So. The Silicon Valley Italian Executive Council was launched in February of 2004 with the idea of recognizing the many achievements of Italians and Italian Americans in the Silicon Valley, some of the great names like Federico Faggin, the microprocessor, Pierluigi Zappacosta and Giacomo Marini, founders of Logitech, Roberto Crea in the field of biotechnology. And we wanted to create an environment to network, socialize, and stay current on technology, the law, and public policy. We also launched a Silicon Valley study tour, which every year brings over some 30, 40, 50 Italian graduate and graduating engineering, computer science, and business students, in addition to entrepreneurs and young managers, and we've been doing that since 2005. And about a year and a half ago, Davide Comazzo used to come to our events, and we started talking, God, it would be great to do something like this in Los Angeles. And I said, I'll give you a hand, and I have to introduce you to a friend of mine who's probably one of the most talented and dynamic individuals with whom I've ever worked, because she was the deputy director of the Italian Cultural Institute in San Francisco. So now she's in LA, and you're really lucky. So I introduced Davide to Valeria, and I think it's been a pretty good partnership, wouldn't you say? And speaking of partners, we are now formally partners, SVIEC and Meet Italy, and we're going to have some joint programs coming up, both in Southern California and Northern California, and I look really forward to that. The partnership is a very important one. We're lucky. California is kind of where it's at in terms of science and technology, and people from all over the world converge upon us, and I'm really excited to be working with you too, and look forward to many great exciting events together, and thank you for having me down here this evening. I love coming down to LA, so this is a great excuse. Thank you.
Thank you so much, Jeff. Actually, it's our pleasure. And with Davide, we were there up north at the last SVIAC event when the mayor of Genova was there, and we gave the same kind of presentation. So this is a true partnership between Northern and Southern California. They're not just words. Now, it's my privilege and honor to invite to the stage my partner and co-founder of Meet Italy, Davide Comazzo.
I understand the last thing you want to hear is another speaker, so I'm going to try to be brief and to the point. And of course, I want to thank our scientists. This is very special to me because I have a natural passion for planets and stars. I always ask my 7-year-old daughter when she comes home from school if she's done any astrophysics. She always looks at me like I'm, a little bit crazy. So thank you for being here. Thank you to ISSNAF for allowing us to have this great pool of talent here. And of course, thanks to the Cultural Institute, which has been a fantastic partner and co-organizer in this Meet Italy journey. Just very quickly, I want to sort of update you on where we stand with the platform, which grows, step by step, event by event. On Monday, when Rampini is going to be here for the night event, we're also going to host an executive lunch with him and a brainstorming session. And then on October 13, we'll be at the Skirball Center. I will be moderating a panel with 3 other professors from Pepperdine University on the stock market and investment issues. And it's the first time that we sort of move out of our home here. We try another venue, and we hope that's going to be a great event. It's a partnership also in that case with the American Association of Individual Investors. Look up our website, meetitaly.net, for more information to RSVP. And then on October 15, we're lucky at Pepperdine at our business school. We'll welcome a lecture from our original speaker and lucky charm, Silvio Angori of Pininfarina. And we're also looking at 2019, we're already laboring on some new ideas, and as Jeff was sort of hinting, there are a few things that are working on. One idea is maybe to have a video-linked event that occurs simultaneously here and in Silicon Valley. So we're working on that. We'll see if we can pull that off. But and also, I would like to thank our commercial partner here for the evening, Veneto Hills, that helps us with the event. And I suppose that's about it.
I would like to add, thank you so much, Davide. You stay here because we have to introduce now. We'll go to our accomplished scientists. Don't forget, please, to RSVP for Meet Italy events, right? Please sign up either on the website or through the invite you receive through the Italian Cultural Institute. So that's the easiest way to do it and most efficient. Now, tonight's moderator and event co-organizer, Dr. Cinzia Zuffada, graduated in electronic engineering from the University of Pavia, specializing in the fields of electromagnetic waves, and completed a postgraduate studies at the prestigious California Institute of Technology. She has worked at the JPL for over 20 years. Her work concerns irradiation models, propagation, and scattering using scientific observation of the Earth. Her career has advanced with various managerial research roles, academic collaborations, and also postdoc programs. Panelist Dr. and Professor Marco Velli obtained his PhD in physics from the University of Pisa at the Scuola Normale Superiore. He teaches space physics at UCLA and works at the NASA JPL. His research concerns the physics of plasmas and the magnetic solar activity, one of the main studies of the Parker Solar Probe mission.
And I would also like to welcome Dr. Sara Susca. She graduated from the Polytechnic of Milan in aerospace engineering and obtained a PhD in electrical engineering from the University of California in Santa Barbara. She has worked at JPL since 2011 in various projects, including the Boston Dynamics Big Dog, the Phaeton Project Stable, and the Europa Clipper mission. Welcome. And of course, we welcome also Dr. Michele Vallisneri, who received his PhD in astrophysics from the California Institute of Technology. He has worked with JPL since 2005 on the international project LISA, revealing gravitational waves. Welcome.
Thank you. Thank you, David. And now, please, as a courtesy to others, we kindly ask you to turn off or silence your cell phones. And now, without any further ado, please give a warm round of applause to Dr. Cinzia Zuffada.
Hello there, good evening. It's exciting to be here. I can see there is a little bit of echo here. All right. Okay, so I would like to bring you into the world of JPL, the Jet Propulsion Laboratory, where we work. And I want to spend a few minutes to just give you a context of what we are about and the many projects that we develop and where our community works. Also touching upon the very important relationship with Italy, with the community that does not necessarily work at JPL but collaborates with us. So we are a laboratory that is part of NASA and also part of a university, the California Institute of Technology. We are 6,000 people. We are located in Pasadena, and we have an annual budget of currently about $2.7 billion. It's primarily funded by NASA, although we do have a component of work which is funded by other agencies. Why Caltech and why NASA? So we started as a laboratory of Caltech in the 30s, where the Army was interested in using the land where JPL currently stands to do a lot of experimental work that ended up then, as World War II approached, ended up in the first experiment in rocketry in the United States. Then what happened was that we developed into what became the civil space program in the country, in the United States, after World War II. And we were responsible at the beginning of 1958, so 60 years ago, for the successful launch of Explorer, which was a first satellite, American satellite that produced scientific results. It helped characterize the Van Allen belts. And so we were in a unique position at the time when the country was going through what became the birth of NASA in July of '58. So JPL pre-exists NASA. It has a very strong relationship with Caltech because we were born as part of Caltech, and we were incorporated into the NASA family towards the end of 1958, but still retaining our own uniqueness and independence. So we are not civil servants. So here is just just to give you a flavor of the many things that we do. I've chosen this slide because it represents a number of efforts for which last year, 2017, there were some very important anniversaries. And as you can see, we work in all segments, all disciplines that are represented in space. Last year we had the 40th anniversary of the Voyager project. So Voyager, the first man-made object that has actually gone beyond the solar system. It left the solar system a few years ago. We also had the 25th anniversary of Topex Poseidon. This is an Earth science mission which helped understand globally the El Niño cycle. We had, the end of the Cassini project. That was a spectacular mission. It had an enormous impact on the public. It ended last year after 20 years. We also had a celebration, the 20-year anniversary of the Mars Pathfinder, so the first small robot that landed on Mars 21 years ago now. It was the size of a small house appliance. It was supposed to be just a demonstration, and it was a successful one, and it led the way to a number of landed missions that continue to this end and beyond, and many more. And many more. New Star is a mission that we have done in partnership with Caltech, our sister organization, to look at black holes. Yeah. All right, so looking to the near future, there is a lot more, and here all that I want to point out is that I have a list of missions that are launching this year, and several have already launched. Some will be landing later this year. The InSight mission to Mars is projected to land in the fall. What I want to say is that in the future, we are also seeing now a movement towards having missions where the spacecraft and the instrumentation are becoming smaller. So we have the first CubeSats at JPL that are going to Mars to do a technology demonstration of communications. So, and with this, I'm hoping to have given you the flavor. You know, Italy is involved in a number of these missions. It has been, certainly in very big missions such as Cassini, for example, and others. I just want to close this segment with a picture here of the Italians of JPL. And as you can see, you know, the Italians of JPL look very young, which is very nice, right? So they represent here a composite of people who were available last week to take a photograph all together. There are lots of employees like ourselves, but there are also lots of students who are interns, who are doing, in some cases, postdocs, and they represent the future of our success, the future of our link with Italy. So without any further ado, now I want to start looking at 3 examples, fields, and stories in more detail. And so let me start by looking at the sun. So it is our star, and I would like to ask Marco Velli now to talk about what he does. And again, there is a strong historical link with Italy.
Thank you, Cinzia. I have a few slides to show. I wanted to give you a flavor and a little bit of ideas and meditations on space, considered to be the final frontier, and the history of space, the sun, and the connections between Italy and the United States, which go back a long time. So let's see if we can get this started. So the image that you see right there is a comet, and it really illustrates space. And I put down the name of Galileo there because comets were in some sense the beginning of his undoing. Galileo thought that comets were an atmospheric phenomenon. And so he wrote an entire book, Il Saggiatore, to essentially ridiculize someone who was not using scientific reasoning, but in fact had a better idea for the origin of comets, and who thought, a Jesuit priest, who thought that comets had to be beyond the moon because of the time it took for them to traverse the sky. Now, Galileo was wrong about comets, but he did have an intuition that what you saw from comets had to do with the sun, and his reason for thinking it was an atmospheric phenomenon was the tails that you see there. And from my point of view, what's more important is that what you see here are 2 tails. And these 2 tails represent 2 completely different things. One is the comet that's evaporating the dust. That's because of sunlight. And then there's a mysterious blue tail that goes straight out. And it shows that space is not empty. So let's see if I can get this thing to work. So Galileo connects Florence with space. He spent time in Firenze. He discovered sunspots. So in some sense, he's the first objective scientist who understood that the sun was not perfect. It's one of the 4 major discoveries, as you know, of Galileo in the year 1609. And Florence has a connection to California which goes beyond Galileo, because another fundamental picture, and I'm going to now skip 3 centuries, is George Ellery Hale. George Ellery Hale was the first person to discover that the sun had magnetic fields, and that in fact those sunspots that had been discovered by Galileo were magnetic vortices. Hale is a fundamental person in that he connects Florence Arcetri with Pasadena, because he was responsible for the 100-inch telescope that was built at Mount Wilson that ended up discovering the expansion of the universe, and I'm sure Michele will be discussing that later. But he also is responsible for the solar telescope and the spectroheliograph in Pasadena, and he donated the construction, the maps, to build this spectroheliograph to Firenze, which then built a very important solar tower that lasted until 30 years ago. So back at the beginning of the century. But let's go back to space now. And this is the solar eclipse that maybe some of you have seen last year. Now this is a photograph from a simple little camera, but your eye, if you've seen the eclipse, does a much better job than a camera. It has automatic filtering techniques that your brain uses that gives you a picture which is much closer to this one, especially if you used binoculars. And that shows you that the sun does not finish at the surface, but expands outward into interplanetary space. And you see that it also has a lot of structure. Well, it was discovered essentially before the Second World War that the temperature of the gas in that region that you see was of millions of degrees. And it became pretty clear that the Earth was not immersed in an empty space, but in something that had to be filled with a very hot gas. In fact, the sun does not end. The Earth is immersed in the atmosphere of the sun. So what happened? In the meantime, we discovered space. This is, I'm showing it because of historical reasons. This is a photocopy from an Italian outreach book from 1947, right after the war. It shows the layers of the Earth's atmosphere and the beginning of space exploration. The Explorer balloons, the V2, which had been brought to the United States thanks to von Braun, the reconstructed V2 that was going to become the basis for the Jupiter and then therefore the launches into space. And it asks the question, what happens out here when you go up above? The temperature first falls, and then it rises again, but he thinks that this is empty space, so it's going to be the absolute void. Of course, in 1957, the Russians launched the Sputnik, and immediately, it was not, so at the beginning, this was really an experimental endeavor, and even in the United States, there was competition between various groups in doing this. So when Korolev managed to launch Sputnik, the day after, Pravda said nothing, because they were interested, but not that interested. But it's when the New York Times published that the Soviets fire a satellite that's received, and American radio aficionados started detecting the ping from the satellite, that the Russians realized that they'd done something important. And so only on Saturday, the day after, did Pravda come out with the news. But the interesting thing for me is that they said this incredible story that's written here, I'll let you read, that satellites couldn't be used for military purposes. They could only be used to study the strange radiation coming from the sun. That strange radiation was of interest, of course, together with cosmic rays, and gave a fundamental input into the development of space exploration. Specifically, in the same year, for the first time, a scientist, Eugene Parker, whom you see here, put forward the idea that the sun didn't end where it ends, but it expands outward, creating a supersonic wind that should invest the Earth. And he gave rise to explanations to lots of phenomena, such as the aurora and other phenomena of that type. Now, his theory was not easy to accept, but we're now at the dawn of the space age, and satellites can end up going there. And indeed, this is what happened. The Russians, so we have 1957 Sputnik, and because of the failure of the Vanguard spacecraft, NASA was born, as Cinzia just said, in 1958. And soon after, in October, the Simpson Committee, which was one of the committees with which NASA was born, we could have a whole reasoning. It's very interesting to follow the logic of how the idea of an independent space agency which does spacecraft for science with committees that have to be independent, with review panels. That would be a whole other discussion, but extremely interesting. At the beginning, the idea of conflict between the reviewer and the scientist was not so clear, what role the scientist should have. All of this came into play with the formation of these committees. But in 1958, it became clear that we had to go to the sun. Excuse me. So the solar probe was one of the things that they thought of, to pass inside the orbit of Mercury to study the particles of fields in the vicinity of the sun. As I said, the Russians were trying to crash into the moon, but they missed. So Mechta, as is favorably known, Luna 1, missed the moon because it's hard to send satellites precisely into space. And it ended up in interplanetary space and gave the first measurements of what is now called the solar wind. This is the measurements made by the Mariner 2, which was also involved with the JPL. And here are the photos of the JPL people that were involved in that mission and their press conference. And this is the speed of the solar wind between the distance of the Earth and Venus. And we see that there's this very fast flow, very hot, hundreds of thousands of degrees, very rarefied, 600 kilometers per second, continuously flowing. Space is not empty, but is filled with the last remnants of the supersonically outflowing sun. So we had to go to the sun to figure out how this works. Why does this exist, and how is it related to the magnetic field? So JPL was involved, and again an Italian was involved. The Voyager owe very much to the figure of Bepi Colombo, who devised the trajectories that could use the various planets to accelerate and deflect the trajectory of a spacecraft to be able to do multiple planetary flybys. In the same way, he devised a way of going to the sun. And his idea, as you can see in Star Probe, was to go to Jupiter, to deflect the satellite and have it fall into the sun. It's very difficult to fall into the sun from the Earth because we're moving so fast around the sun ourselves. And that idea was further developed over the years, but all the time technology was just one step ahead of the probe itself. The cost and the technology required to do this was one step ahead. So here we go from the late 70s to the 80s to the early 90s. And then finally, in the first 10 years of 2000, we realized that we couldn't go to Jupiter. We did not have the capability of doing the spacecraft by going to Jupiter, and it was not feasible, and it was not technology interesting to go all the way to Jupiter, fall into the sun, take measurements for a few hours that we wouldn't really understand anyway because we were going so fast. So we developed a new probe, and this is when I became involved, which uses Venus in the same way that Bepi Colombo had wanted to use Jupiter. We use Venus, and we rotate around Venus very quickly, 7 times to go closer and closer, like Icarus, to the sun. So this is our discussions of our group with Eugene Parker, who has become a good friend now that we are deciding to launch a probe that has his name on it. So this is the night of the launch of Solar Probe. We had a long conversation. And this is the launch. It's always fascinating to witness a launch. And I'll just let you see this for just the beginning of this at least. This was the 3:50 a.m. on August 12th this year. So Solar Probe is on its way to Venus to, for the first time, go into the atmosphere of the sun.
With NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the sun.
Cape Canaveral. So Kennedy Space Flight Center. So let me go forward. That's the beautiful launch of probe, which is working well. And I will close showing you the magnetic activity of our star and how close the probe will actually go and what it will see flying through the solar wind, the bursty and still not understood solar wind.
Thank you, Marco. And now let's take a look now in the outer planets of the solar system, and in particular to a satellite, right? So let's talk about Europa.
Yes.
And Sara has a lot of interesting things to tell us about the Europa Clipper mission and her particular path.
Yes.
Yeah.
I'll
You
wait for
start and I'll put it up.
Okay. So I've been working on JPL for a few years, and I changed a few roles. And lately, I've been in the role of system engineering, which doesn't mean much, but I'll tell you what my life looks like. When everything is going fine, I don't exist. And then when something goes wrong, where is she? So it's always when something goes wrong, the system engineering really kicks in. And so Clipper gave me the great opportunity to understand this role and learn how to be calm and just paddle under the water. Okay, so I'm gonna be talking to you guys about Europa. So the Europa Clipper mission is an awesome robotic mission that goes back to what the mission of really JPL has been, which is really explore with, not with humans, but we, of course, with robots. And the Europa is a small moon of Jupiter, is the size of our moon, but contains as much water as Earth. And the way we know that is because a long time ago, there was a spacecraft that went there, Galileo, and on board on Galileo, there was a magnetometer. And Galileo was passing by, and there was a blimp. There was a blimp that the magnetometer scientists could not understand. And as they looked at it and said, wait a minute, there must be water in there. Not only that, there must be salt in it. So the way the scientists started looking at this moon was like, wait a minute, we thought we were alone on this, in the solar system. We were looking for life way out there, and we have so much water here. So Galileo was instrumental to make Europa that big of a deal for anybody looking for life in any form. So we don't have a life detector. We wish we did. So we can't go there and find life, although we do always joke about we have whales. We think there are whales there, but that's an internal joke. So, and we are gonna go and take a picture of it. So, but there are things that we can look for, and is Europa habitable? So there are 3 ingredients that we think are important for something to be habitable, and that's water, and we know it has a lot of it, right? And then energy, and it got to be there because Europa has this thick crust of ice, and then there is water inside above a rocky core like our planet Earth. So there must be some sort of way, and of course, definitely the tidal from Jupiter is creating heat, but something else that keeps this ocean warm. And because there is salt, we know there is chemistry happening. So radiation from outside is creating some molecules, and as the ocean and the ice talk to each other, right, exchange, this material can go down. So there are ingredients that we believe are key to find life. So that's why we're going there. That's why it's so exciting to go there. So our spacecraft it's a beast. So it's pretty much, the spacecraft per se, the body is pretty much as big as a school bus. And in fact, you can see the scale, the high gain antenna, which is this dish right there. And it's how we're gonna talk home most of the time and exchange a lot of data. It's 3 meters, so that's quite big. And the solar panel are so big, they are tip to tip, 30.5 meters. They're so big we can't open the boat at the same time on lab. There is no place we can deploy. We can only open one at one time. And for system engineers that want to test everything, it's a big deal. So we have a lot of instruments, of course, because we are going there to explore. We want to understand, so we need to go there all geared up. And so we have instruments that look at, we're called basically RAM instruments. So as the spacecraft flies like this in the ionosphere, we try to sniff as much as we can, right, or the particles that are there, so we can understand the composition of the ice. And so we have PIMS, mass specs, and SUDA. So they're really trying to understand the composition both of the surface as well as the ions that are floating around that Jupiter is also influencing. And then we have nadir instruments. So as we fly over, so these instruments are cupping and sniffing, but there are other instruments looking down and try to take as many pictures as we can. And we take them in different spectrum, because some certain things are not visible, in the visible spectrum, which is our eyes, but are visible in UV, which is shorter wavelength, or further out thermal. So we are really trying to understand how much we think there are going to be some sort of icebergs there. So we want to understand how they move in and out, because we think there is exchange between the ocean and the ice. So that's what they are there. And then we have the reason antennas. So the reason, it's an ice penetrating radar. Of course, we want to understand how thick the surface of the ice is. And the ice mag, again, we cannot go there. We learned the lesson with Galileo. Don't go there without a magnetometer. All right. So how long does it take to get there? It can be a very long journey. So we are pretty big, as I said. The spacecraft, it's 6 metric tons, and with propellant and everything. Otherwise, if you eliminate that, we are 2.5 metric tons. It's like an SUV. So we have a Delta IV Heavy and Falcon Heavy, and those, although they are big guys, they won't get us there in short time. So we need to get a few slings passing by Venus and Earth a few times to get there. So 7.5 years, which is a long time to wait. And then, of course, if we want to go this way, we can take us only 2.5 ways. It's pretty much the freeway of planetary traveling, and it's an Oman transfer from Earth to Jupiter. So we like that a lot. Everybody does. So it's really, really hard to send a spacecraft to Jupiter. Fundamentally, one of the biggest challenges you have to deal with is radiation. I mean, I always think about Jupiter as this little unfortunate radio star in a way, and it's just like spitting out as much as radiation as it can. And in Europa is actually quite close to it. So because of that, if we were there, we would die within a few minutes. And the electronics, don't do that much better. So we have to take a lot of care to make sure that electronics on board can survive the time that we need to. And we have very limited power. You've seen the solar array are huge, just ginormous. And the sun is so dim, and we are always so cold, so we are fighting continuously. Do we have enough energy to stay warm, and do we have enough energy to run the instruments? So it's very challenging. And then, of course, we have this hurry up and slow down mission, because if you see these pedals, so let me show you. So you see this. Let's see. Okay, this is Jupiter, and these are various moons, and this is the Europa orbit. And these are our pedals. So the way the spacecraft can survive in the radiation is actually stays away and then goes in when the radiation is high and gets out of it quick. So that's how we do it. But any pedal lasts 2 weeks, and we are close to the moon for hours. So it's like nothing happens for 2 weeks, and then you collect all the data, and then you get the data back, and if something went wrong and to change something in the instrument, you need to wait 2 more weeks. So it's not, you can't do all the things that you do when you are orbiting constantly, like we do in other missions, like Mars, for example. But we will get incredible images, 25 meter per pixel resolution. It's like if those pictures were available of Earth, which they are classified. So imagine how detailed we're going to be able to see the icebergs there. All right? So fundamentally, I like those big questions I was raised with a lot of philosophy. So for me, it's like, where do we come from, and where we are going is important. And there is a new one that, another one that I learned as I moved along in my career, and is, are we alone? It became an obsession. And Europa Clipper, again, we don't have a life detector, but he's looking into one of these aspects of it, and right in our own home, in our own backyard, which was not thought of, even 20 years ago or so. So that's why it's so cool.
Thank you.
Thank you.
Now, with Michele, so we want to go out of the solar system, go really far, far away, right?
Right.
And we talk about the search for gravitational waves.
Thank you. So it seemed appropriate to start just this few minutes of a chat with a brief biographical note. And just today, in thinking about it, I realized that today, to the day, is 20 years since I landed here in California to come to graduate school. And I think on the first day I went out and I bought some cereal, some milk, and some peanut butter, because it seemed appropriate. And that was the start of my experience here. But so I was raised in Parma, Italy. I was raised a theoretical physicist at Università di Parma. And so the reason I came to Caltech for my grad school was space-time, I guess, in the fundamental theory of what space-time is, the fundamental theory of gravitation that Einstein gave us. It felt very philosophical, but I knew that coming to Caltech I would be able to temper that with an engagement in an experiment, which was LIGO, looking for gravitational waves. I'll tell you in a minute what it is. And then the next step was to JPL, so just a few miles up the hill from Caltech, and the reason for that was not space-time, was space. Yeah. Space as in outer space, as the place where we put missions, because that's the ultimate frontier, as I will tell you, to look for and detect gravitational waves. So I had this very philosophical mind and build, but at JPL I met this very exciting place of engineers who actually put things into space, and I soon came to envy them a little bit, because I was there looking for the big questions, but they were making these super cool things, you know, that go to Mars and that people drive on Mars, and to this day, even witnessing, as an astrophysicist, witnessing, you know, solar system physics and solar system exploration is one of the thrills of being a JPL. But the story I followed is a story of 100 years, actually a little more. I'm not going back to Galileo, since you did Florence, and you should, you know, you're from Tuscany, so that belongs to you. But, you know, Einstein, 1905, with special relativity, he redefined the very notion of time. He told us that time is not absolute. Simultaneity, which is what I thought, you know, I experienced when I called my parents home. I thought I was simultaneous to them. Well, Einstein would teach you, no, you're not. You know, everybody carries their own time and their own watch. And there's no way to extend that across space more than a few, you know, kilometers, or and there's no way to know that you and somebody on the other side of the solar system are simultaneous. Beyond that, Einstein wanted to start to describe gravity, not just time, and he had this intuition that to describe gravity, he needed to bring together space and time and to make them into. He didn't so much worry that they were not empty. But what Einstein realized is that they're alive, in a way. They're dynamical. They're not just a stage where, you know, the theater of physics happens. They actually can change, can move, can warp, you know. He didn't have the math to do that, and he got his math from Gregorio Ricci-Curbasto, who was an Italian mathematician that I had the pleasure recently to study in some depth, because I wrote a mathematical appendix for a biography of Ricci by Judith Gustin, who's at Caltech. Ricci was amazing, but what he did is he built this field and this theory of math that didn't really have an application. So, you know, there's a review in 1901, and people say it's beautiful, but it's not really so useful at this point. But it was just what Einstein needed. So when Einstein got to Zurich in 1913, he met his friend Marcel Grossmann, and Grossmann told him, here, look this is just a math that you need to describe space-time as something that's changing and that can change. And we know this because Einstein, together with Darwin, but Einstein more than anybody, I think maybe the human being whose mind has been dug into with the most detail. So we have a project, the Einstein Papers Project, with over many years, you know, dozens of scholars who have looked into every single thing that he wrote. And in particular, there's a notebook, his Zurich notebook, where every page, you know, they went into every equation and and understood it so they really knew what he was understanding, what mistakes he made, how he got to everything, and it's fascinating. Anyway, so what he got to is that space-time is dynamic, and the changes in space-time create gravity, the curvature, if you wish. Space-time is curved, and that's what gravitation is. So it's not really about forces. It's not the sun pulling on us. The sun curves space-time around the solar system, and all that Earth can do, trying to go straight, as Galileo taught us, all that Earth can do is just to go around, because that's the straightest way possible. Now, if space-time is alive like that, you think that it could also entertain something like waves, so that if you can ping on space-time like a bell, you'd have some kind of oscillations, and that's what gravitational waves are. So this is just a graphic. This doesn't try to be accurate in any sense. But if you take two massive, heavy bodies, typically we like to use black holes, because stellar origin black holes are the heaviest, the densest objects in the universe, and you send them around each other, well, they create ripples in space-time that eventually get to Earth, and that we can try to detect. Einstein saw this. He came back and forth on whether they were really physical, but in the end, he thought it was an actual prediction of his theory, but all he knew about things that go around quickly was Mercury. Pretty much. That was the fastest thing you know about. And Mercury is not too heavy. The waves from Mercury are completely undetectable. And even if he had the notion of a black hole, he couldn't have figured that the technology 50 years later, no, 100 years later, sorry, technology will get to the point where you can measure infinitesimal, I shouldn't use the word infinite, very, very, very small, deformations in space-time. So the event that we saw in 2015 from two black holes, I'll tell you in a minute, changed lengths here at Earth by a part in 10 to the 21. So that's it. Over a length of 4 kilometers, the change in the length was of the order of 1,000th of the radius of a proton, okay, of a nucleus, which is ridiculously small. And the reason is that, although space-time can be curved and warped and deforms, it is exceptionally stiff. So you need a whole lot of energy to be able to bend it or warp it just a little bit. And the energy that was coming to Earth from this event that was so hard to detect was actually equivalent to the moon's, the full moon's power. So like 1 watt per square meter, something like that, which sounds like that even our eye can do for light, obviously. We can read with full moon light, yep. But if you need to use that to make gravitational waves, super weak. And again, Italy comes into it. So these are the original Fermi boys, the ragazzi di Via Panisperna. And the one in the middle is Edoardo Amaldi, who was the founder of many things, an extremely important person for Italian, European, and universal science. He was the co-founder of the Istituto Nazionale di Fisica Nucleare in Italy, of CERN, of the European Space Agency. He really, Fermi had left for the US, and also he died very young. Yeah. Edoardo Amaldi was the rebuilder, one of the rebuilders of Italian physics after World War II. And he was part of the reason why, when I left Italy 20 years ago, I felt that physics was an Italian thing. I was proud of not just the Italian contribution to physics over many years, and I was proud of the formation that I had received in Italy. So Amaldi had ideas to look for gravitational waves using the instrument at the bottom, which was a resonant bar. The idea, if you have a very pure and big chunk of metal, effectively, in a pure geometrical form, gravitational waves passing basically excited like a bell. And with very sensitive detectors, and if you keep it very, very cold so that you don't get much vibrations from thermal effects, you can hope to detect them. There was a false alarm, in fact, not from one of Amaldi's instruments, but it was Joe Weber in the US building also this kind of resonant bar detectors, and he claimed to have detected gravitational waves in 1962, I think, or 63. So those claims were not credible at the end, but they started the whole experimental field of trying to do something, to see something that Einstein thought would be impossible to see. And what it took eventually is this kind of detectors. So these are the Italian Virgo near Pisa. Yeah, I do. Yeah, I should have gone to Pisa too. and the two American detectors, LIGO, in Louisiana and in Washington. The idea here is that these are big laser interferometers. You take a lot of laser light, you split it into two beams, you send them across perpendicular paths, and when you recombine it, you can use laser interference to see if one of the two arms is a little shorter than the other one, or a little longer. If it is, you don't get perfect cancellation of light, you get a little signal, and that's what tells you that gravitational waves have been seen. And now Virgo and LIGO have been proceeding together. They started in the 80s as projects, they started construction in the 90s, and LIGO beat Virgo just by a few months. So Virgo was not on at the time of the first detection, but it caught up quickly, and only the next year was able to see a signal together with LIGO. So that was the now famous waveform that was seen by, it's technically called a chirp, because it sounds like whoop, which is what some birds do. And what you see there is the translation into gravitational waves of the finally spiral emergers of two black holes. The Times itself had a cover for it, and rightly putting Einstein in the corner, because exactly 100 years later, this was the culmination of something that was born as mathematics, as a physical intuition, with Ricci's mathematics. And then it took 100 years to realize that it was really physics, it was really something that's truly in the universe, to come to have the technology needed to see it, and to understand the astrophysics of systems that could produce this phenomena. And this is, again, it's a simulation, but it's a visualization of what the source would have been. These are two black holes. You don't see the holes, but you see the deformation and the bending of the stars behind them. It's a binary, so they're going around each other, just like the Earth goes around the Sun. But in this case, as they go around each other, they're bending space-time, they're emitting energy into gravitational waves, and they're losing energy, so the spiral gets faster and faster until they merge and they become a single black hole. This happened 1 billion years ago. It took 1 billion years for these waves to come to Earth, and it was finally seen into using ground-based detectors. Now, I said I went to JPL for space, and that's because, skipping over this for a second, it's because there's a whole spectrum of gravitational waves. The ones that we've seen, finally, after 100 years, are in the same frequency range of sound, effectively sound that we can hear. So the noise, the chirp that you heard, whoop, was actually the straight translation of that signal into audio waves. But if you can listen, if you can look for things that are changing more slowly, if you can look for frequencies that are not hertz, so once per second, but things that change once every hour or every 10 hours, you can hear bigger black holes. Black holes like the big million solar mass black hole that sits at the center of our galaxy. You can see this, you can hear this across the universe, and this can help you do a lot in terms of understanding a universe, understanding how galaxies grew and merged and lived together with their black holes, can help us understand cosmology and measure, do a cosmographical measurements of the universe. And to do that, you want to go to space, you want to have something that is not LIGO or Virgo 4 kilometers wide, but you want to go millions of kilometers away, with 3 spacecraft that are exchanging, once again, lasers. That's the best way to measure distances. And so 100 years from Einstein to the detection of gravitational waves. This mission, LISA, started as an idea in the 1970s. It was studied many times. Right now it's finally approved. It's as a mission led by the European Space Agency. NASA is committed to participating as a junior partner, yet a crucial partner, and the current launch date is in the 2030s, okay, 2034. So, 20 years I've been here, 100 years for Einstein to get confirmed, 40, 50 years for this mission to get made. So there's a reason I'm envious of the Mars people who get to go every 2 years. At the same time, I'm very proud to come from societies such as Italy and Italian research. that had gave itself the time and the ambition to try to do these very long processes, and to be in a place like JPL that is doing the quick Mars things, but it's also looking forward to the 2030s and to take the long view and doing this kind of science. And I think taking the long view is a good thing in many in many fields. I'll let you imagine which ones, but again, we can do it, and we're doing it at JPL, and I hope we can do it in Italy and in the US. Thank you.
Thank you. We have gone over our allocation, and so I would recommend that we reserve questions of the panelists or myself in the second hour. So there is more outside. We have posters where you can learn about some earth science that we do at JPL. And we have big data, and we have a movie from the rover roving on Mars. So thank you. I hope we were able to give you a sense of our own universe, our own trajectory, and bring you into our experience and interest you to perhaps learn more, want to know more. Thank you.